So in the last video, we talked about matrices and how a matrix, an n by n matrix, tries to work on a 1 by n column vector as an operator to give a totally different vector pointing towards a different direction. But we also talked about some exceptional cases where the vector does not get transformed in its direction, but just changes its magnitude, that is, it scales up or scales down. And those are the eigenvectors of that matrix. In this video, we will elaborate on the concept of eigenvectors, that is the vectors that do not change in direction, and its eigenvalue, that is the value by which the vector gets scaled after that operation.
So let's have a quick look at transformations. I have a two-dimensional space again. I have my basis vectors and I have an arbitrary vector pointing at an arbitrary direction. Focus on the direction though. Now I'm going to do a transformation on these coordinates and let's see what happens to this vector. Well, as you can observe, as I'm doing this transformation, this vector has completely changed its direction from its original position. Although since this is a linear transformation, it is still pointing at the same coordinate axes. But main thing here to observe is that the direction has changed, and that means this is not an eigenvector. But now, let's see a different scenario about different vectors. So now here, I have two different vectors here pointing at, again, some different directions. And let's do a similar transformation and let's see what happens to these vectors. So well, as you can observe, as I'm transforming, this vector has not changed in its direction, and neither has this vector changed its direction. But these two vectors have scaled up and scaled down in its magnitude. So now, these two vectors are the eigenvectors or eigenfunctions of this certain transformation that I'm doing. So there's a matrix operator somewhere which is doing this transformation on this coordinate axis. And these two vectors are the eigenvectors of that operator. Now let's see how to calculate the eigenvector for any other matrix operator or any other operator in general.
So calculating eigenvalues is easy. Let's try to consider a random matrix 2, minus 2, 2, and 6. And let's try to operate it on this vector x and y. X, y. And by the definition of eigenvalues, when I try to transform this vector with this matrix, the output should be the same vector but scaled by a factor. And let's say my output will be that same vector but scaled by a factor of lambda, which is the most common notation to state the eigenvalues. Control engineers also call it S, but this is the same thing. And S or lambda can be a complex number too, but it should involve rotations at that point. Let's talk about rotations a little bit further. Let's try to focus on this example. So if I have my matrix A and x bar, then this will be equal to lambda times x bar. So this equation is important because anytime you want to calculate the eigenvalues with a matrix, well, this is the formula that you should use. So now let's calculate, let's try to bring this in the same direction, same side. A x bar minus lambda x bar equal to 0. So A minus lambda, I can't do A minus lambda, so I have to multiply lambda with an identity vector since lambda is just a scalar, times x bar equal to 0. So now x bar cannot be equal to 0, so my A minus lambda I should be equal to 0. And if my A minus lambda I equal to 0, that means the determinant of the A minus lambda I should be equal to 0 in one dimension. So let's do it here. My A minus lambda will be 2 minus 2, 2 and 6, minus lambda I will be lambda, 0, 0 lambda, which is this A minus lambda I, times x bar equal to 0. So now this matrix should be equal to 0. So that means 2 minus lambda minus 2, 2 and 6 minus lambda equal to 0. So its determinant, let's try to calculate its determinant now, which will be equal to, lambda square minus 8 lambda plus 12 minus 4 plus 4. So lambda squared minus 8 lambda plus 16. And it's a good equation because now the roots I have is just lambda minus 4 squared equal to 0. Or my eigenvalues are lambda equal to 4. Well, it's very easy now. Because when I get my value of lambda, I can just substitute the value of lambda here, times x bar equal to 0 to calculate what my eigenvectors will be. So now, let's substitute the value of lambda as 4. I get 2 minus 4 minus 2. Minus 2. Well, let's rub this. 2 minus 2. 2 and 6 minus 4 is 2 times x and y equal to 0, which will be minus 2x minus 2y equal to 0 and 2x plus 2y equal to 0. So my set of the equations, so this is my eigenvectors, so I can again simplify as x plus y equal to 0. From these two equations, I can deduce that this vector is my eigenvector for this matrix transformation, or x equal to negative y. Graphically, x equal to negative y, so technically this is my eigenvector. So when I try to apply this transformation, this vector will not change in its direction. It will just scale itself by a factor of 4 every time I do the transformation. So this is my eigenvector. Well, x equal to negative y. More practically, let's take another example. Let's say I have a cube this time. So let's say I have a three-dimensional cube or space, whatever, and I'm applying force on this cube. I'm applying force in this direction and this direction, such that the cube will get stretched. Now the cube can be considered as a three-dimensional space with origin in its center and vectors spreading all across the space here. So here's a vector, here's a vector, here's a vector, everywhere. And after stretching, the cube will get deformed. And let's say I can get something like this. I'm applying force in just horizontal direction again. So this is my deformed cube. But now every vector, most of the vectors will get changed, and will change their direction after I apply the force. So this vector will be this vector, which is actually now pointing in a different direction because the cube's dimensions have changed. The cube's lengths have changed. But there are also some vectors that will not change in its direction. For example, this vector and this vector, this vector, this vector, and in z-axis. But let's consider this vector and this vector. So these two vectors, since our force is being applied in this direction, these vectors will not change in its length, will not change in its direction, but only change in its length by a factor of lambda, which will be more than 1 this time. And these vectors too, the perpendicular vectors to the force, will also not change in its direction, will not change in its length either. That means this vector, this vector, this vector, and this vector are actually the eigenvectors of this transformation where I'm applying force in both the directions. One of the applications of the eigenvectors. There are many more applications of the eigenvectors, but first, let's talk about what would happen if I include pure rotation. Let's consider an example. Alright, so let's try to consider pure rotations, and let's see what happens to our operator matrix when I try to find the eigenvalues for pure rotation operator. So from the last video, you may have known that if I want to consider pure rotations, the formula that I should be using is cosine theta, sine theta, negative sine theta, and cosine theta, where theta will be my angle of rotation for a certain vector. And if I operate it with a vector, let's say x and y, then by the definition of eigenvalues, I should get lambda times that same vector x and y. So now let's try to operate on this important equation. So now I can take the lambda minus IA vector. Let's say cosine negative sign. I'm omitting theta for now, but understand, when I just write cosine, it's cosine theta. Sine and cosine minus lambda times the identity vector, lambda 0, 0, lambda equal to 0. To find the eigenvalues first, so now I can write this vector as cosine minus lambda, negative sine, sine, and cosine minus lambda. And the determinant of this matrix should be equal to 0 to get the eigenvalues. So now the determinant of this vector will be equal to cosine minus lambda square, cosine square minus 2 lambda cosine plus lambda square plus sine square. Or I can simplify this equation again so that I could write cosine square plus sine square is 1. So lambda square minus 2 lambda cosine, okay, let's write theta now, 2 lambda cosine theta plus 1 equal to 0. And this is my characteristic equation. It's hard to write like this. Okay, so now this is my characteristic equation. And now let's try to find the roots of this equation, because again, we are actually considering pure rotations. So for example, if I have a two-dimensional space, I have a vector, then after transformation, this vector will purely, or let's say I have x and y, after transformation, the whole coordinate axes will get rotated by a certain angle. So if I consider 90-degree rotation, for example, then this will be my x, this will be my y, this will be my negative x, and this will be my negative y. Similarly, this will be my transformed vector. So let's try to consider this equation again. This is a quadratic equation, so it won't be difficult for us to find the roots by using the formula. So minus b, which is 2 cosine theta. So let's again write cosines, just let's ignore theta, plus or minus square root of b square, which is 4 cosine square, minus 4 divided by 2, which will be cosine theta, plus or minus, let's say 4 gets out and gets cancelled with 2, so a square root of cosine square minus 1, again sine square plus cosine square equal to 1, so cosine square minus 1 equal to negative sine. So cosine theta plus or minus square root of negative sine square theta are my roots of this equation. Or I can also write cosine theta plus or minus I sine theta. And this is actually a complex number. The derivation is very beautiful, because when you try to find the roots of the or the eigenvalues of pure rotations, what you get is actually the complex number, which is cosine theta plus I sine theta, where theta is our angle of rotation. Or I can also write in the phasor form as e to the power plus or minus I theta, where theta again is my pure where theta is my angle of rotation. Let's consider an example a little bit further, but I have an exercise for you guys. What if I want to also scale this vector? So now let's say this is my 1, 1 vector, and after some angle transformation, I also want to scale this vector 3, 3 after rotating the whole axis. Now again, let's try to consider, okay, hold on. Let's go back to our cube example. Which has its own coordinate axis. So what I'm trying to do here, while pure rotation, I'm just rotating this cube somewhere else. So I'm just rotating this cube such that if this is x and y, then after rotation, I'm gonna get the same shape of the cube. But now this is gonna be my x, this is gonna be my y, and so on. So I have not exactly scaled anything, I have just changed the perception of the view of this cube. And that's why I say that this transformation is actually imaginary, because I can just view this cube like this, and this is gonna be my same cube. That's why I say, that's why maybe I like to call it that this transformation is actually imaginary. But again, that's why pure rotations have pure imaginary eigenvalues. But what if I also want to rotate this cube, and I also want to stretch this cube by some factor? So my x, y. Then what will be my matrix? And by what scalars will I have to multiply this matrix to make sure that actually I get a complex number? Well, I want to scale this cube. So let me know in the comments by solving yourself if you have any matrix like that in mind. Let's get some more examples. Alright, so last example, and this is my favorite one. What if I try to include the rate of change or time in this whole equation? That is, again, if I have some value x, it can be any parameter. And what if I try to track the values of x with respect to time? And try to bring in differential equations here. That is, if I have, let's say, dx over dt, that is rate of change of x, as a function of x. So let's say minus 2 times x. And this is my equation, a first order linear equation. So what this says is that as I increase the value of x, the rate of change is going to keep on decreasing, and eventually it's going to reach 0, the rate of change. So now let's try to work on this equation. So 1 over x dx equal to negative 2 dt. So ln of x equal to negative 2t, or x equal to e to the power negative 2t. And if I try to bring the initial conditions here, e to the power 2t will be multiplied by value k. And this is my final form of this solution of this equation again. And again, intuitively, I can also say that as I increase the value of x, since I have a negative value, I can say that the rate of change of x, that is the slope of this equation, is gonna eventually decrease. So my graph will be something like this. And this will be, let's say, some value. But again, as t reaches infinity, my x will reach 0. And this is what I want you to grasp. More general form is that x will be equal to c1 times e to the power lambda 1 times t, where lambda 1 is the eigenvalue. And since this is the first order equation, you can also relate this to like the capacitor equation if you have studied circuits. So if this is my voltage and I'm trying to measure the voltage increasing with time, then my voltage will be V of t as a function of time, V naught times e to the power negative t over RC, where RC is the time constant. So through initial conditions, this will be my V naught. And I can say that this system is stable. That's what engineers do. They make sure that the eigenvalue is negative. That's why we can also assure with that as the time goes to infinity, the slope will eventually reach 0. A more profound way is if I try to include inductors in this context, or RLC circuits, I will get a second order equation. So if I try to bring it a second order equation, I can get C1 e to the power lambda 1t plus C2 e to the power lambda 2t. And then I will get a little bit oscillation or a damped circuit or a damped response, where I will get something like this. But eventually it's going to reach to 0. And this is one way of the writing. And this is one of the most important applications of systems, where we try to make sure that the eigenvalues are negative, which also makes sure that the slope will eventually reach to 0. And that's how we can conclude that the system is stable. Let's talk about this in a different video, because this video has already been long enough. And I'm pretty sure that I have explained the concept of eigenvalues clearly and the method to calculate eigenvalues in this video. So in the next video or in some other video, we will talk more about the applications. For now, I want you to grasp that if the eigenvalues are negative, then the system is going to be stable. And if the eigenvalues are positive, then exponentially, I'm going to have an exponentially increasing response. And eventually the system will reach instability. So that was it for eigenvalues. If there's anything I may have missed in this video, please let me know in the comments and I will make a separate video about it. If you have any doubts, please let me know in the comments and I'll respond to you. For now, thank you very much for watching. Subscribe for more. My name is Abhishek, signing off.